Today we're going to be talking about sampling distributions and estimators and getting a little into the central limit theorem. The sampling distributions of a statistic is the distribution of all values of the statistic when all possible samples of size n are taken from the same population. The reason that we take sampling distributions is because samples are easier to get than a census, and for certain statistics, the values target that of the entire population. I'll go into a little bit more detail about what we mean by this in a second. Statistics that target the population parameters, those where the sampling distributions would be useful, are for the mean, the variance, and the proportion. One easy way to remember these I like to use is the ones that you can be targeted. We call them the MVPs because it's mean, variance, or proportions. The statistics that do not target the population parameters are the median, the mode, or the standard deviation. With any sampling distribution, we sample with replacement so that we have independent samples. So I'm going to take a little bit and talk about what we mean by what we just wrote so we can kind of understand. When you think about a question like, what's the average weight of a male in the United States? It's really hard for us to get that value because if we were to get that true parameter, what we would need to do is we would need to weigh every male in the United States, which would be very hard to do. So what statisticians do instead is they start sampling groups of males. So I might grab a random sample of males and let's say I find their average weight is 170. Then I take another group and I find the average weight of these people is 150. Then I might get a really, really heavy group and I find their average is 210. And then what happens is I keep sampling and you keep sampling. And as you sample, you may get a light group, but you're going to grab a group of, let's say, 20 males, take their weight and average it up, and then you plot it on this distribution. Get another average of 20 people, get another average of 20 people, and then what happens is you start getting numbers that repeat. So like I might get another 170, I might get something light, and then what tends to happen here is you just keep doing this process over and over again. So as we continue to draw samples, of this time it's size 20, and you keep plotting those, what you end up with is these distributions start to stack. You start to get some numbers more than others, and it will start to resemble a normal distribution. You see this shape right here? So after a statistician is able to sample enough, what they do is they take all of these groups, so they've taken a bunch of groups of 20 and averaged up the weights and then plotted them. And then if you actually find the mean of this distribution, this will get you to whatever the mean is of the population. So let's say it's something like 167.5. If we just sample and keep sampling, the central limit theorem tells us that as we continue to sample, we're going to get a better idea of what the actual mean weight of a male in the United States is. This is why we are allowed this is why we have the MVPs, so we can do this process with mean, variance, and proportion. This process that I just described down here, this will not work for the values for median, mode, or standard deviation. So taking this a step farther, we're going to take a look at some applications of the central limit theorem. We know that if we know the distribution of a population and we know its mean, then we collect all samples of size n from the population and calculate the mean of each of these samples. The distribution of the means will take on the shape of a normal distribution. If the original population has a normal distribution to begin with, like IQs or heights, the mean of this means that the sample size can just be 1. You can just grab one group of people and work with this. If the original population does not have a normal distribution, the sample size must be at least 30. This means that we would need to get at least 30 groups of people before we would be able to see this. Generally, the distribution of the means of the samples will be much narrower and steeper than the distributions of the whole population. We'll see this in the following example. We can easily calculate the mean and standard deviation for the sample means distribution. the mean is going to stay the same. So whatever the mean is of the population is the same. But the standard deviation for the sample mean is going to be slightly different, because what we're going to want to do is we're going to want to take the standard deviation that's given to us for the population and divide that by the square root of the number of items in our sample. So again, let's take a look at an example. Heights of males in the U.S. In the United States, men's heights have a mean of 69.2 and a standard deviation of 3. It is also known that the heights of males in the United States is normally distributed. So this means that since it's normally distributed, we don't really have to worry about the size of the sample. So first we're going to look at the probability that if we randomly select a single male from the U.S. population, that their height is between 66 and 71. This is exactly what we did last week in 6.2 and 6.3. So what I'm going to do here is we're going to shade this. So 66 is right here, 71 is right here. And you can see we're going to have a pretty good amount of this graph shaded, right? It's going to be this stuff in here. So now using the Excel file, let's find the probability that if we randomly select one male from the U.S. population, that their heights are between 66 and 71. So this is the inequality that we're looking at here, is 66 to 71. We want the height to be between those values. And now I can't show this on the video, but I'm going to go to that Excel worksheet and we're going to make sure we select in between, right? So we're working with our normal distribution Excel. We're going to be doing in between. And so I'm going to put my lower bound of 66, my upper bound of 71, my mean of 69.2, and a standard deviation of 3. And when I do that, I find that this shaded area is 0.5827, or the probability of selecting a single male between that value is about a 58.27% chance. Because again, you take a look at it, I could select somebody who is really tall, I might get somebody that's really small, but it's most likely that I'm going to select somebody in here that's about a 58.27% chance. It says, now what is the probability that if I choose 16 males in the from the U.S. population, that the average height of those men will be between 66 and 71. So now I'm not just selecting a single person, I'm going to select 16 people and average their heights together. Notice I didn't make the number that I needed of 30, but since my population since heights are normally distributed, we're not too concerned about the size of the sample. So what is the probability? So do you think the probability will be greater than or less than the problem that we did above? I'm going to give you a second to think about it. Just put an answer of what you think will be the case here. Do you think it's going to be a bigger number than 58.27, or do you think the average heights of these people is going to be a smaller percentage? All right, let's keep going with this. So using the information discussed when using sample means, we need to adjust the standard deviation. So we're going to be using this formula right here. So what we're going to do is the standard deviation for our sample means is going to be, the old standard deviation was 3, right? And then we're going to divide that by how many members are in our sample. Well, it tells us right here again. It is 16, so we are taking the heights of those 16 people. Now this is a square root, right? That should be in your calculator. If you can't find it, ask me in class. But we're going to take the square root of 16, which gives us 4. And then on top, that 3 carries over. So our new standard deviation is going to be 0.75. So this is the standard deviation we're going to be working with for the average of 16 males. So now I'm going to take a look and we're going to actually find that area. Here's the distribution that we're working with when we have a sample distribution. So between 66 and 71, take a look at this. Look at how much more of this area I'm going to actually be shading, right? It's all this stuff right here, right? So 66 to 71 is all this stuff right here. So again, let's figure out the probability. It's the same inequality, right? 66, x is between 66 and 71. We're going to select the in-between, but just make sure that we're going to now be using this new standard deviation of 0.75. So I'm going to go to my Excel spreadsheet. We're going to go to in-between. The A is going to stay the same at 66. The B is going to be 71. The mean is going to be 69.2, but this time I'm going to change that standard deviation to 0.75. And this time, I get something pretty different. The area that's shaded, or the probability that 16 people will have a height between those values, is 0.9918, or 99.18% chance that the average. Now, why is this the case? That's because, let's take a look back at our single distribution. This is just one person, right? So again, it's not out of the question to have one person who's super tall. But when you take the average, when I average up 16 people's heights, the outliers are going to kind of wash out, and most people are going to be falling in this range. So this distribution is much more narrow. So which was greater? It's the group, right? And the reason is because I'm averaging 16 males' heights instead of just one male, so the fact that the average is going to probably lay closer to the mean. So here's where I like to put this all together, and hopefully this makes sense to you. It says the following distribution for selecting a single person's height as well as selecting 16 people's heights and finding their average. What do you notice about the two distributions? So you can see the red graph depicts the if we average up 16 people's heights, and the green distribution is just selecting a single person. You see that these are both normal distributions, right? You also can see that 69.2, that's the mean for both of those. That's the center of both of these distributions. But the red distribution is so much more steep and narrow because when you average up 16 people's heights, again, it's not so likely that you're going to have cases where it's 74 or 61. That's not unlikely to select a single person in those values, but to average 16 people's up and have their average be that high or low value, it's going to be pretty unlikely. So the means of both distributions is still 69.2, right? That's what I said. That's the center. The distribution for the average of the 16 males is more steep, right? And this is because the standard deviation sorry about the handwriting, is smaller. Remember, let's go back and take a look. The standard deviation of the 16 males was 0.75. What does that mean? That means it's a smaller spread of data compared to the other one. The standard deviation of the population is 3. So that's why our green distribution is much more wide.